Hello, I'm Mark Unkefer, Executive Director of the Fiber Optic Sensing Association, and welcome to our webinar with SAMM Technologies. We're really excited to hear from them. It's a great reminder of both the versatility of the technology, but also its global nature. And just a word of apology for those who were signed up before. We have had to delay this webinar because of some technical issues, but let me assure you it will well be worth the wait. So I won't introduce all of the folks from SAMM. I'll let Bulent Toksoz do that, but he has a number with him today, and we look forward to hearing more about how fiber optic sensing is used in Istanbul and kind of a case study. So Bulent, we look forward to hearing from you.
Thank you, Mark. Hello, everyone. This is Bulent. For some, good evening. For some, good morning, and have a good day. And I would like to welcome you on our webinar on fiber optic distributed acoustic sensing for active seismic monitoring. And before that, I would like to welcome you on behalf of our company, SAMM Teknoloji. And I would like to start with a very quick introduction video.
As SAMM Teknoloji, we offer products and solutions minding two questions. What does a customer want? And what does a customer really need? SAMM Teknoloji aims at the highest level of competence of all its employees in the workflow. And as a result, customer satisfaction is efficiently achieved. SAMM Teknoloji is a Turkish company founded in 2003 by 4 engineering friends who believe that the engineers and technicians of this country can create world-class values. Since being registered as an R&D center in 2018, SAMM Teknoloji has developed multiple projects in various fields, including fiber detection technologies, all by cooperating with many research institutions and universities. Eventually, the outputs of these projects has been transformed into commercial products. SAMM Teknoloji is among the first Turkish companies to specialize in interconnection passive equipment in the telecommunication sector, known as connectivity solutions. It is also the approved supplier of the European Nuclear Research Center, CERN, whose headquarters are located in Switzerland. Our company's name has become an exemplary and pioneering brand in the sector, providing cost and time advantages in various projects, and also adopting the new movement of domestic production. SAMM Teknoloji is one of the companies that completed most of the work on data centers in Turkey. It works with all mobile and landline telecommunication operators, as well as corporate data centers, system integrators, public institutions, and public organizations. SAMM Teknoloji, which is the main distributor of Raspberry Pi in Turkey and other different development cards and robotics products, offers online sales and engineering services of electronic product groups for education and R&D. In addition, with the sense of responsibility for being a main Industry 4.0 and robotics products and services provider, SAMM Teknoloji continues to deliver its informatics products to any point within Turkey. As a result of the cooperation agreement signed with TÜBİTAK Bilgem in 2019, a fiber optic-based distributed acoustic detection system, Fotas, was developed and commercialized by the SAMM Teknoloji R&D Center. Fotas is a system that detects acoustic signals formed around a fiber optic cable. It classifies these signals with the help of a developed artificial intelligence software and gives an alarm to the end user. In addition, SAMM Teknoloji continues its R&D studies on fiber optic-based distributed temperature and voltage sensing, also known as FBG-based single fiber sensors. Regarding the heating and heat tracing sector, SAMM Teknoloji has signed for the application of many electrical heating projects since 2006, especially in the industrial and commercial areas. As SAMM Teknoloji, we continue to expand our fields of activities with our creative, experienced, and dynamic staff.
Well, this is a case study from Istanbul, and Turkey is located in a highly active seismic zone, and it is known for being an earthquake-prone country. This is due to its location along the Anatolian plate, which is being pushed eastwards by the Euro-Asian plate, and it results in frequent earthquakes. And the North Anatolian fault zone actually includes a segment known as the Marmara segment. It runs through the Sea of Marmara, and it has been identified as a potential seismic hazard for the region. And the most recent major earthquake in the region was the 1999 7.4 magnitude of earthquake, and it caused extensive damage and loss of life in the Istanbul metropolitan area. Well, to understand the behavior of the Marmara segment and improve seismic hazard assessment, and as well as the mitigation strategies in the region, an R&D project for the earthquake early warning was initiated by Istanbul Gas Distribution Industry and Trade Incorporation, namely İGDAŞ, with the support of Istanbul Metropolitan Municipality and Energy Markets and Regulatory Authority. Well, this project started in September 2022, and it is expected to be completed in December 2024. İGDAŞ's position as a pioneer actually deserves recognition in this area, and I really applaud it. Within the project, SAMM Teknoloji provides its fiber optic distributed acoustic sensing system product, namely Fotas, for real-time seismic activity detection and analysis. It will provide valuable information for earthquake early warning systems. SAMM Teknoloji is also developing artificial intelligence to analyze the large amounts of data which are generated by the fiber optic system. And our AI will identify the patterns and trends that may indicate seismic activity in the region. In this regard, we have a reputable university in Turkey, Boğaziçi University, and it is Observatory and Earthquake Research Center called Kandilli Institute is a partner of the project. Well, the Kandilli is with 155 years of success, and it is very well known in Turkey for seismology. And with its special expertise in evaluating the data gathering for this project, this institute also contributes significantly to the project. Well, distinguished audience, I would like to give the floor to the Director of R&D at İGDAŞ, Kadri Buldanlı. And Mr. Kadri Buldanlı, the floor is yours.
Thank you, Mr. Bulent. Hi, this is Kadri Buldanlı, and I'm the Director of R&D in İGDAŞ, Istanbul's gas company. We are doing gas distribution to 60 million people with 7 million subscribers, and we are among the first 6 big city distribution gas distribution companies in the world, and we are distributing around 7 billion square meter of gas every year. And it is our pleasure to be here today and to discuss our efforts to ensure the safe supply of gas in Istanbul, which is a city with a high earthquake risk due to its geographical location. There is the location of Istanbul is close to the fault lines. We have to work tirelessly to ensure the safety of Istanbul citizens. And we already have a system, gas system, which we call earthquake early warning and risk reduction system, which allow us to cut the gas supply in case of an earthquake from the regional generators, 832 regional generators around the city, by using SI sensors located in each one of those generators, regulators, and this way we can cut the gas supply in case of an earthquake. But we wanted to do furthermore, and we started to work on a new project, which is fiber optic based early warning and monitoring system. And we are working with SAMM, and we are working with SAMM on this project, also with Kandilli and another company. And we are trying to use the fiber optic lines located in the bottom of the Marmara Sea to early detection, for the early detection of the earthquakes, and it will allow us 3 to 30 seconds earlier detection than the SI sensors located on the shore, which will give us some opportunity to take measures like stopping the trains or those kind of stuff, or cutting the gas earlier to reduce the collateral damages which can cause by earthquake. By detecting seismic waves on the ground of the Marmara Sea, earthquake data will reach our system earlier than the standard accelerometers on the coast, as I said, and in this way, critical systems will be able to shut down earlier, and it will be possible to mitigate the collateral damages. However, we recognize that only the infrastructural efforts will not be enough for our city. Therefore, we have implemented earthquake awareness project to increase public awareness about the earthquakes and educate people about what to do in case of an earthquake. Also, to take necessary precautions to minimize further damages in such case. At İGDAŞ, we are constantly working to become more prepared for a potential earthquake, and it's not only for Istanbul, it's also for all the cities surrounding the Marmara Sea. The system will serve all of them, and we hope that our efforts can contribute to the safety of the citizens around these cities and also around the world. Thank you for your time, your participation, and your interest. Mr. Bulent, you can take over.
Thank you, Mr. Kadri. So now I would like to give the floor to Professor Ali Pınar from the Kandilli Observatory and Earthquake Research Institute.
Bulent, perhaps Professor Pınar's microphone is mute, and we may want to move on.
Okay, I have just noticed that it's mute. Okay,
Yes.
I will start from the beginning. Sorry. I am Vice Director of Kandilli Observatory and Earthquake Research Institute and Professor at the Department of Earthquake Engineering. And Kandilli Observatory operates a seismic network where the stations are deployed all over the country. We operate more than 250 broadband short period and strong motion stations all over the country. And most of the stations are actually located around the Sea of Marmara. We operate about 100 seismic stations located as free field stations. And most of them are comprised of strong motion sensor, also broadband sensor are co-located at some regions. And also Kandilli Observatory operates stations within the city. We have more than 100 strong motion stations within the city, and the aim of operating seismic stations within the city is for rapid assessment in case of large earthquake. So the damage will be assessed immediately after if major earthquake happens, and the most damaging or the ground motion where the amplitudes were higher or the PGA values were are observed at maximum, those regions will be immediately informed to the municipalities, responsible people, and so on. And Kandilli Observatory is enrolled in fiber optic project that is run by İGDAŞ, and our aim is, our major aim in the project is to share the seismic station that are very close to the fiber optic cable, also to share data that are around Marmara Sea, and also Kandilli Observatory and Earthquake Research Institutes actually operates an early warning system in Marmara Sea region, and of course we will try to use data from this early warning system also. In my presentation, actually, I will try to answer the question why the fiber optic system was deployed in Marmara Sea region, and the main purpose for monitoring using fiber optic cable is that the North Anatolian Fault crossed the Marmara Sea, and although we have several seismic stations around Marmara Sea, at present we don't have any OBS, ocean bottom seismograph station, and in this sense, the fiber optic cable is the only sensor that is crossing the faults that are expected to be ruptured by the major earthquake that we expect. In Marmara Sea, actually, the North Anatolian faults comprise of a few segments that are expected to be ruptured. For example, one of the fault that is called main Marmara fault constitutes of two segments. One is called the western segment, the other is called the eastern segment. And actually, the major earthquake that is expected in Marmara Sea is probably will take place with a rupture on at least two segments. Let's say the eastern segment of main Marmara fault, and the other segment that is also expected to be ruptured by the major earthquake is the Princess Island segment. And these two segments, that is to say the eastern Marmara main fault segment and the Princess Island segment that is located in Çınarcık Basin, is very close to the fiber optic cable, very close. I mean, the fiber optic cable cross these two fault segments that are expected to generate major earthquake. And one of the segment that is expected to be ruptured is the Princess Island segment. And the fiber optic cable is crossing the Princess Island segment. We can see in the next slide the geometry of the fiber optic cable. And next slide, please. Yes, here the red line indicates the location or the geometry of the fiber optic cable. And as you can see, the PI, that is stand for Princess Island segment, the fiber optic cable crossed the PI segment, and also the fiber optic cable crossed the eastern segment of main Marmara Fault. And these are the two segments that are expected to generate the major earthquake. And that's why I think the location, the geometry of the fiber optic cable is very good. I mean, it's perfect in the sense of early warning studies, because the closest stations are located onshore, and the onshore station, and the distance of the onshore station is more than 20 kilometers to the fault. In this sense, we can gain at least 4 or 5 seconds for early warning studies, because the fiber optic is located just above the fault to be ruptured. And that's all actually the contents of my presentation. Thank you.
Professor Pınar, thank you so much for the background information and all the related information as well. Now I would like to give the floor to SAMM Teknoloji's manager of the R&D, Mr. Erkan Ozkan. Erkan give you some detailed information about our DAS works for this project. Erkan, the floor is yours.
Thanks, Mr. Bulent. Hello and welcome everyone. Thank you for joining us today, and welcome to our webinar. My name is Erkan Ozkan. I'm the manager of R&D at SAMM Teknoloji, where we develop fiber optic sensing technologies and IoT products. I am thrilled to have all of you joining us today, as we are excited about the fascinating world of DAS and its applications in seismic monitoring. Seismic activity, with its potential to impact communities and infrastructures, is a critical area of study, and DAS has emerged as a cutting-edge technology that is revolutionizing the way we monitor and analyze seismic events. Traditional methods of seismic monitoring have their limitations, but DAS offers a game-changing solution. With DAS, we can transform ordinary fiber optic cables into a vast network of seismic sensors, enabling continuous real-time monitoring of seismic activity with unparalleled precision and detail. As you may know, fiber optic sensing works by sending pulses of light through a fiber optic cable and then measuring the changes in the reflected light caused by the movement of the cable. When an earthquake occurs, the seismic waves cause the ground to move, which in turn causes the fiber optic cable to stretch and contract. These movements causes changes in the light that is reflected back to the instrument, which can be used to measure the magnitude and duration of the earthquake and also localize the epicenter. Fiber optic sensing can be particularly useful for monitoring large areas, as the cable can be installed over long distances and can provide continuous monitoring of seismic activity. This technology is still relatively new and is not yet widely used for earthquake monitoring, but it has the potential to provide valuable insights into earthquake behavior and could help to improve earthquake forecasting and early warning systems. Previous slide, please. Mr. Bulent. Yes. Fiber optic sensing has several advantages over traditional seismic monitoring techniques. For example, next slide, please. Okay, it can provide continuous monitoring of large areas over long distances, which can be useful for detecting small earthquakes or for monitoring the behavior of larger earthquakes. Secondly, it can provide more detailed information on the movement of the ground, such as the direction and duration of the seismic waves, which can be useful for understanding the behavior of earthquakes. And also it is less susceptible to noise and interference from other sources such as traffic or human activity. Of course, for a seafloor deployment, which can make traditional seismic monitoring more difficult. Next slide, please. Okay, what do we do so far? In Tavşantepe, Pendik, we have successfully installed the fiber optic-based acoustic sensing system that we call it Fotas, utilizing the existing fiber optic cable, originally designed for communication purposes. We have extended its functionality to monitor the seismic activity. The fiber optic cable spans a total distance of 60 kilometers, passing through Büyükada before reaching its endpoint in Ambarlı near Avcılar. As Professor Ali Pınar previously highlighted, the fiber optic cable has been laid in close proximity to the fault line in the Marmara Sea. This fortunate positioning allows us to closely monitor seismic activity in this high-risk area using the fiber optic cable-based system. Our installation includes not only the Fotas system, but also a powerful server equipped with extensive processing and storage capabilities. This server plays a crucial role in efficiently handling the massive amount of data generated by the system. It enables us to process the data in real time, store it for short-term use. We also utilize cloud services to store the processed data for future use in artificial intelligence trainings. This robust setup ensures efficient data management and enables us to leverage advanced AI techniques for enhanced seismic analysis and prediction. After installation of these devices, while continuously monitoring the fiber optic line, we also started the geographical calibration of the system. We match the GPS coordinates where the fiber optic cable passes with the fiber optic path length, of course, where we can do that. Next slide, please. We have integrated earthquake information from established seismic systems, such as AFAD, Ministry of Interior Disaster and Emergency Presidency, and Boğaziçi University, Kandilli Observatory and Earthquake Research Institute into our system. This allows us to automate the process of seismic activity data recording by utilizing the data gathered from these sources. By incorporating data from these reliable seismic systems, we can enhance the accuracy and comprehensiveness of our seismic monitoring, analysis, and recording processes. Next slide, please. The data we gathered from the system is not always perfect. There are some challenges we have to face with. As I mentioned in previous slides, we can easily do the GPS coordinate to fiber length matching for the segments of cable that is not inside the sea. We have approximate location of the cable at hand for the undersea parts of the cable. In order to accurately localize the epicenter of the seismic activity, we need to have a good reference, which is not available right now. We will use the conventional seismic activity monitoring instruments such as force balance accelerometers to calibrate our geographical layout of the fiber optic cable. Another challenge we are facing is fiber optic coupling to the seafloor. Some parts of the cable is not well attached to the seafloor. This causes blind spots in the data we gathered. The other issue we are facing is optical losses of the cable. We use an existing fiber optic cable. By the time it was laid, I think it was perfect, but now there are splices on it. Next slide, please. This is the waterfall graph, the earthquake that is occurred on 9 of March in the Marmara Sea near Erdek, that has a magnitude of 4.2. The x-axis is the time axis and the y-axis is the fiber optic path length from the interrogator. The color shows the intensity of the received signal. Please ignore the first few kilometers, since it is not under the sea, and these are due to the traffic or some other noise sources. You may see there are some blind spots which appears horizontal lines that is insensitive to seismic activity. Next slide, please. However, we can clearly identify the P and S waves of the seismic activity. P waves are also known as primary waves because they are the first waves to be generated during an earthquake and are the fastest. They are longitudinal waves that propagate through the earth, causing particles to move back and forth in the same direction as the waves travel direction. S waves are also known as secondary waves because they are the second waves to be generated during the earthquake and arrive after P waves. S waves are transverse waves, meaning that they cause particles to move perpendicular to the direction of the waves travel. Unlike P waves, S waves cannot pass through liquids and they only propagate through solid materials. As a result, S waves are responsible for the up and down and side-to-side motion felt during an earthquake. They are typically slower than P waves, but their motion is more intense, causing more severe shaking and damage to the structures. Because they have different speeds, we can estimate the distance of the epicenter to each segment of the fiber. By using intelligent triangulation and array processing algorithms, we will estimate the location of epicenter with high accuracy. Next slide, please. Before going on with the seismic activity detection details, I want to show you the graphs obtained from the system for the devastating earthquake happened on 6th of February in southeast of Turkey. We are working on the collected data to better understand the behavior of the system for such a destructive event. I am also severely sorry about our more than 50,000 losses. Now I will give Tayfun the floor and he will talk more about the AI and signal processing parts. Okay, Tayfun, floor is yours.
Okay, Erkan, and thank you, and hi everyone. I'm Tayfun, and I am the Senior R&D Engineer at SAMM Teknoloji. Now, I will continue to share with you some information about artificial intelligence. We are trying to use some artificial intelligence in algorithms and methods, and we already have experience in using DAS. AI algorithms can be trained to recognize these patterns in dust data that are indicative of seismic activity. Seismic waves generated by earthquakes typically exhibit distinct patterns of amplitude, frequency, and duration. AI techniques such as machine learning algorithms will be trained on labeled dust data to recognize these patterns and automatically detect these seismic events in real time. So for label this data, we create some tools to label these species signatures and these patterns. AI algorithms will be deployed to process dust data in real time, allowing for rapid detection and response to seismic events. This will be important and crucial in the early warning system, where timely detection of seismic activity can enable prompt evacuation or other preventative measures. Already available in our integration tools, that this can happen with network interface or something can be triggered, actually. It's important to note that the effectiveness of AI-based seismic activity detection using dust data depends on the quality and quantity of the data available, the accuracy of labeling and training data, and the robustness of the AI algorithms used. Proper validation and testing of the AI models are necessary to ensure their reliability, and accuracy in the detecting seismic events. So next slide, please. Okay, some common signal processing methods used for calibrating DAS systems for seismic activity monitoring. In the simplest form, bandpass filtering is used. DAS systems may pick up noise and other unwanted signals that can affect the accuracy of the seismic measurements. Bandpass filtering is a signal processing technique that can help to remove noise and isolate the seismic signal. Noise reduction techniques are also applied to improve the signal quality. These algorithms will allow us to see P and the S waves that Erkan mentioned and demonstrated before, and clearer from noise. Last but not least, a novel wavelet denoising algorithm is used to improve the signal quality also. Yes, next please. And also we use spectral analysis in order to analyze the frequency contents of a signal. This can be useful for identifying specific frequency ranges that are of interest of seismic monitoring. For example, certain frequency ranges may be associated with specific types of seismic activity, such as earthquakes or industrial vibrations. We do the spectral analysis using techniques such as Fourier transform or wavelet analysis. At the end of all this, after the data has been well analyzed, these will be leveling and the earthquake detection problem will be solved first. And then P waves will be discovered in advance. After the accuracy is increased, the artificial intelligence will provide us with the information from which channel or location the wave came first. In this way, we will make a great contribution to the calculation of things such as size, location, and the development of the early warning system. Next, please. As Mr. Bulent mentioned before, the project started on September 2022. The project is a 2-year project. Now we are working with the academicians and the industrial bodies to develop this system. And thanks for your participation. Thank you for listening to us. So I'm leaving the word to Mr. Bulent now.
Well, thank you, Tayfun. So we have concluded the project presentation. I will be very happy to answer your questions if you have any. And by the way, you can always email us, as you can see on the screen, for any reason. Mark, it's on you.
Thank you very much. And we do have a number of questions. I want to kind of perhaps do an overview and let Bulent let you kind of do it. What are some of the key advantages for DAS for seismic monitoring, and are there any limitations or challenges associated with the technology?
Okay, so Erkan, maybe you can answer this question.
Of course. So the main advantages of the DAS technology for seismic activity is we can have multiple sensors along a line. So this is a unique feature that cannot be replaced by any other technology. And also we can monitor the undersea seismic faults, and this is easily done by using fiber optic cables laid underground. So also we can use array processing in DAS data for accurately localize the seismic event. So these are the advantages for seismic monitoring of DAS data.
And a follow-up question to that is, obviously there are other sensors that are available. So how is DAS integrated into those monitoring tools such as seismometers and GPS to provide kind of how shall I say, a comprehensive look of the current seismic status.
Of course, the other sensors, the GPS or the accelerometer sensors, also very good for seismic monitoring. And these can be integrated into a comprehensive system to make an early warning system, because we can have a fiber optic cable laid for 100 kilometers or very long distances. For other sensors, you have a point sensor, so you need to have individual sensors laid by a distance. But for the DAS systems, you will have a continuous array of sensors that can be used for accurately localize the seismic activity, and also it can be integrated into the an comprehensive system by using our integration tools to monitor the fault lines.
So one of the fascinating takeaways from all of this is appreciation for the sort of how critical seconds are for a gas distribution company to be able to take steps to avoid a broader, bigger calamity when an earthquake is detected. Wonder if I could go back to the CEO of the gas distribution company and kind of talk about sort of what can be done in those seconds, and how is it the seconds matter so much? Obviously, we appreciate that you're kind of stopping the flow, but can you elaborate a little bit on how that how sort of that benefit proposition of being able to take advantage of those extra seconds?
Hello, let me try to explain it. As I told you, we already have an early warning system which cut off the gas. And our problem with the gas companies is not the cutting off the gas, but giving it back. Because we have to knock every door and we have to make sure that the gas ovens and everything is off before turning it on. So what we can gain by that, those 3 seconds or 30 seconds, we are a company which is owned by the Istanbul municipality. And what we can provide here is not only for ourselves, for İGDAŞ, but we see an opportunity to help other people. For example, for the firefighters, we can open the doors before the earthquake. So in case of an earthquake, the cars won't be stuck inside. Or we can stop metro trains, which are going with 80 km/h speed during the earthquake. But if we can reduce their speed or stop them before the earthquake, we will save the life of everybody inside. Or similarly, we can turn on the generators on the extensive care units in the hospitals. Those are the things that we can do. It's not only gas. And for the gas, it's important for us because like we are putting our system into an alert position, and we are stopping the gas in every neighborhood. Only there is a very strong shaking at that area. Otherwise, if there is no danger, we will keep providing the gas. But if there is a risk, we will stop it. And this is what we can do as the gas company. So we are going a little bit further than our own role, and we try to help all the people around it. Thank you.
That's very helpful. So in effect, what you're describing is a smart city application, obviously specific to gas distribution, but with multiple additional advantages that sort of once you know that you've got the warning, then there are other uses that are available. Now, could you elaborate a little on how you share that information with those other, how shall I say, stakeholders, those other beneficiaries of those early warnings? Do you have, you must have developed some kind of alert system to share that information so quickly?
Like we have an advantage with the fiber optic cables, because the fiber optic cables provide us the data with the speed of limit almost. And also what we are going to do, like using the other fiber optic cables crossing the Marmara Sea, we will give the alerts to each city around the Marmara Sea, because like if the earthquake is close to Istanbul, it's far from, let's say, Tekirdağ or Bursa, or in another way, if it's close to Tekirdağ, it will be close. It will be a good early warning for Istanbul. So we will try to create a network of communication to provide each city municipality about the early warning system, and we are working on it with the artificial intelligence, and it will take some time. We are also working on it, and first of all, we have to end this project and get the results that we want at the end of 2024. And at the same time, we are working with the Istanbul municipality to develop such a system parallelly. In parallel.
That's very helpful. Let me go back to Bulent, and I don't want you to have to tip your hands, but clearly this is a particular application that could be used around the world. Without tipping your hat, are you looking at other municipalities that may be similarly situated where such an early warning system would be extremely beneficial?
Yeah, like it will be extremely beneficial. I know that many countries in the world right now is working on those systems. They are not finalized. Istanbul has a different structure, as the Marmara Sea is so close by and the fault lines are so close by, and as we can place the fiber optic cables on the fault lines, we have some, you can call it advantage in this matter, but disadvantage towards the earthquake. So like it can be used in other cities also. Like if we can be successful on that, we will be glad to work with other cities to provide that because like I will say it's not as our position as the gas company of the Istanbul, of the city, and as a part of the municipality, we are not just trying to keep it for ourselves, and we want to share it with other cities also.
Right. So that's actually a very helpful distinction to draw, which is that you were able to put it right on the fault line, whereas, for example, California with multiple fault lines, you know, while there may be some fault lines that they can put fiber optic cable along, there are those that they can't anticipate or don't anticipate, and that therefore they wouldn't get quite as long a warning time. I guess that's it's kind of belaboring the obvious there and the point that you made.
And like also there's a limitation of 50 kilometers because or 100 kilometers for the fault line for fiber optic cable to work at the moment. I hope that in time we will work on that and we'll make it longer, and it will be an advantage for everybody.
Well, thank you very much. And I will say that we've actually exhausted the questions and discussions that we've gotten so far. So for those who did ask about the availability of the webinar, it of course will be available on the FOSA YouTube page along with our other webinars. And those are always a great, even for those who have participated live, a great opportunity to listen again and perhaps pick up additional details that may have slipped through. So for all of the team in Istanbul and SAMM, from SAMM, we thank you very much for this presentation, and this concludes the webinar.
Thank you.